Welcome everyone to the Progress and Prospects in Biology webinar series. Thank you for joining us today. Today is the 9th lecture of the Saturday special lecture series, and we are delighted to have Professor Amlan Chakrabarti from A.K. Chaudhary School of Information Technology, University of Calcutta. For the participants, please feel free to post your question in the YouTube chat box and we will moderate them towards the end of the session. And the feedback link will be posted in the YouTube chat box and it will not be shared via email. For those who are new, please subscribe to our YouTube channel and follow us on Twitter, Facebook, and Instagram pages. Please do watch the archived videos in the YouTube channel as well. Now I would request Professor N.R.A. Banerjee, the convener and mentor of the webinar series, to welcome our speaker. So, ma'am, over to you.
I think ma'am has some issues with her internet. I guess she's got logged out. We'll just wait for a few minutes.
Hello?
I think ma'am has got logged out somehow.
Okay.
So we'll just maybe wait for over 2 minutes.
Sorry, I was disconnected. Nandita, what am I supposed to do? I'm supposed to say. Our computer sciences professor is our speaker today, and I have failed to be here on time because of an internet glitch. So apologies for that. So a very warm welcome to all our listeners from around the world. This is our Saturday special lecture of Progress and Prospects in Biology. And as you know, we try to sensitize you to how the field of biology is rapidly changing. And with the unprecedented amount of data that is being generated in the field of biochemical networking, molecular biology signaling, in cell biology, in the different types of biological moieties that are constantly bombarding to evolve in ways that are quite unconceivable. So I guess the human mind has devised newer ways to deal with the kind of data that requires deep learning. And today our speaker is going to tell us about that. So a very warm welcome to our speaker tonight, Professor Amlan Chakrabarti, who is going to share with you how other disciplines are foraying into biological sciences, into new findings of biological sciences for an interpretation like never before. Data extraction, understanding the relationships between the different kinds of data that are coming up, which are very, very heterogeneous in nature, requires quite a radical deviation from traditional modeling and conventional way of analyzing how biological moieties react external stimuli to each other and change themselves and others in the process. So a very warm welcome to our speaker tonight. We are delighted to have you with us, Amlan. And I think
Thanks,
today
Professor
what talk about is something that students of biological science probably even a decade ago could not imagine. So without further ado, I would request our host and moderator tonight, Nandita, to please introduce our speaker, and we are all waiting with bated breath to listen to your talk. A very warm welcome.
Yes, ma'am. So, Professor Amlan Chakrabarti is the professor and director in the A.K. Chaudhary School of Information Technology at the University of Calcutta. In his academic career, he has done M.Tech from University of Calcutta and PhD from Indian Statistical Institute, Kolkata. He has done postdoc from School of Engineering, Princeton University, USA. He is the recipient of prestigious DST Boyscast Fellowship Award in Engineering Science 2011, INSA Visiting Faculty Fellowship in 2014, JSPS Invitation Research Award 2016, Erasmus Mundus Leaders Award from EU 2017, Hamiad Visiting Professorship from University of Cambridge 2018, and Shiksha Ratna Award by Department of Higher Education, Government of West Bengal in 2018. He is also the senior member of IEEE and ACM, Secretary of IEEE CEDA India Chapter, Vice President of Data Science Society, and life member of CSI India. He has published around 150 research papers in refereed journals and conferences. His research areas are quantum computing, reconfiguring computing, embedded system design, VLSI design, computer vision, and machine learning. So without any further ado, I would request Professor Chakrabarti to take over. So over to you, sir.
Yeah, thanks, Nandita, for this brief introduction. And thanks, Professor Banerjee, for inviting me to this excellent forum, which I find is a great place to be, because as I know, this is a pretty interdisciplinary platform where researchers, scientists from the various disciplines coordinate and communicate, and to just to explore the possibilities they can contribute in the field of biology. So so that gives me an immense pleasure, because that means I studied biology up to my 10+2, but after that I didn't got the chance to do so due to my career, in the college and university career. But I was very impressed when I tried to look into this domain. Okay, and it's really fascinating because. So I will give you a little brief that when I visited the Department of System Sciences in Kyushu University, Kyushu Institute of Technology as a JSPS fellow. So there I find that the department name is the System Sciences, and the department hosts faculties from computer science, from electrical engineering, from mathematics, and as well as biological sciences. So because the belief is that the most complex machines in the present world are the biological machines, and what we're trying to do, being a computer engineer, a computer researcher, from my practice, what we're now trying to do, we are now trying to build machines which can have some sort of functionalities which a biological object can have, and that is a really fascinating, as Dr. Banerjee told. And what I am also looking into the aspects of data and how we can build models to predict the different detect and predict the disease conditions of an individual. So, without not wasting much time, I will just go straight into the topic. I will try to keep my lecture around 1 hour. Right, I feel in the virtual platform that's the most optimized schedule. But obviously, I will be very open to questions after my lecture, and that can go on for some time. So I feel that I am audible to all of you, and my slide is visible to all of you, right?
Audible. You're audible, sir, and slide
Perfect.
is perfectly visible.
Okay. Perfect. Okay. So the title of the talk is AI and ML techniques for computer-aided disease detection and diagnosis. So AI means artificial intelligence, which is a particular domain by which we try to build intelligent systems, and ML or machine learning is a type of tool by which we try to implement artificial intelligence. And obviously, the path progress of ML. At the present scenario is also deep learning, which is the advanced form of machine learning. My talk will try to focus on one aspect of AI and ML in the biological sciences, though there are many more, right? but as I am not expert, okay, of the other domains where AI and ML are being used for biological sciences, I am trying to give you my experience, or the domain I have gained uh, certain good results, okay, and just try to share with you what are the background of those understanding, and then I will focus on some of the works that we did, right, and obviously I will try to focus on the next level of activities that I foresee. So this is the agenda of my talk, which will start with some introductory concepts of medical imaging. That's the predominant source of information of the work for computer-aided detection and diagnosis. And then I will come to what are the formal premises of the computer-aided detection and diagnosis. Then I will follow up with a brief introduction of AI and ML and how it works well with the CAD. Then I will give a brief introduction of the way the traditional ML and the deep networks can converge and can, okay, so either we can step up from traditional ML and move to deep networks, and what are the advantages we get in those type of deep network functions. Then I will discuss with you only some of the activities. We have done a lot of activities in this domain for the past 6 years. Okay, I started this domain, working in this domain pretty in 2014. But due to a limitation of time, I will not just go into all the applications what we have done in our research. Okay, some few interesting case studies I will discuss, and then I will conclude my lecture. So, so the domain of, okay, AI and ML in biological sciences, what I work with and what I am trying to convey to you is the domain of medical imaging, right? And it is a very fascinating domain, we all know, and I think the scientists or researchers or students from biology are more knowledgeable in this domain. But what I have learned and what I have tried to gather the knowledge in this domain through my deep interactions with a lot of doctors and biological experts. With that knowledge, I will try to explain what is the computation challenges and what I foresee as a medical image as a data, and how I can use it for computation processes for a better outcome of the society. So the medical imaging is something, a non-invasive way of understand or collecting the data of a disease condition of a body, right? And it is so much popular because it is non-invasive, and also it gives a great insight, okay, of the structure, of the shape, of the size, and also in some cases it also gives you the way you can understand whether the structure is changing with time or not. So the phenotypic expression of the structure is very well understood to this particular domain, though the domain is pretty complex, right? And I am not an expert of medical imaging also. I just work with the data what a medical imaging expert gives to me, and then I try to analyze that data with my algorithms. But I know, or what I understand is that it is a pretty complex domain, and we know that it actually it's a multi-scale, right? It goes into various scales, right? You can have images in the microscopy, you can have images from the radiology, you can images from the nuclear imaging sources, which are different type of sources, different scales of the data, different types of organs they try to capture, right? And different types of dynamics, right, inside in the human body, because we know that there are rigid organs, there are non-rigid organs, and for rigid organs, there is some sort of some process of imaging. For non-rigid organs, there are some other different processes of imaging. So there is a amount of variability. Okay, and this essentially looks into the another part of the data science, which is called big data. Okay, it actually is a big data because thinking the number of patients we have in a city itself. Okay, if I just consider the number of patients in a city, okay, it's a big data problem. We don't have to go farther to the number of patients in a state or a country or a geographic zone. Okay, if we just try to take the data of the patients in a particular city, it's a huge amount of data, which has a huge variability, which has a huge variation among, which is a huge, okay, as an increase in terms of the time, which is called the velocity of the data, right? And also it has multiple dimensions, which gives the large data space to convert. So this type of so medical imaging is a one way. It's a fascinating in terms of the technology by which the image gets captured. Okay, but it's really a complex domain when we try to understand the data without the help of an expert like a doctor, right? So I will try to come to that why it is a so challenging problem. So we know that these are, so this, first of all, these images are captured, and then they are stored, then they're analyzed. Okay, so either the doctor analyzes that with his or her eyes. That means he or she goes to the computer terminal and tries to go to the image. Or the other way is to help the doctors, whether there can be some automated analysis of the images, right, to give some useful insights, okay, to help the doctor to save his or her time. Or in some cases, it can also help the doctor to have a secondary opinion, right, from the automated process of analysis, right? And considering the country like India, okay, and many countries where we have less number of doctors and many large number of populations to cater, this is indeed a very useful way of analyzing and helping the doctors to have their time in a more effective way for the different classes of patients, right? I will go into deep onto this in the latter discussion also. So as I told that it is a really a big data type of data repository. If we see that the entire imaging modalities, right, it goes into multiple scales, it goes into multiple functionalities or multiple type of the organs it tries to capture the information. So basically the term modality for our imaging actually is coined to understand or to try to capture the different functionalities or different features, okay, of the body organs. For example, okay, just from my knowledge point of view, what I understood by speaking with the doctors is that suppose you have a tumor, okay, which is there in any body organ. The predominant feature is the size of the tumor. If the size of the tumor is it's over a threshold, normally it is considered that the tumor is a higher chance of being malignant. Okay, vis-a-vis a tumor which is small or very small, that is considered as a lesser chance of getting malignancy. But in the other way around, when the doctor wants to see the functional imaging like PET, okay, a structural imaging is something like CT, MRI, or X-ray. But a functional imaging is something like PET. When the doctor But this particular small tumor, if it is functionally very active, it means it's doing a metabolism at a very high rate, right? It can be a very that means it can have a higher chance of being malignant. So what the doctors uh, uh, do, okay, they actually try to now go with the structural and functional information of the structures, and that's why you have some of the modalities which capture the structural information and some modalities which carry the functional information. From the structural information also like when you try to compare between CT and MRI, the okay, so it depends on what type of structures it can give best results. So CT can give very good results with the tissues which are which doesn't contain much water, right? It actually works in that process. It is basically a sort of X-ray which uh, gets absorbed if uh, there are muscles or there are soft tissues, right? So, sorry, which gets passed when there are muscles and soft tissues, and which get absorbed when we have the bones like calciums. Uh, so, so it doesn't gives a very good information about the very soft tissues, okay, like the tissues what we have in the brain. Vis-a-vis MRI works with the energy oscillations of the water molecules, and that gives a very good information about uh, the type of the soft tissues of the body, okay, like brains. So similarly we have sonograph, the ultrasound type of techniques which actually goes for uh, dynamic movements in the body, where it not only gets the information of the structure, but it also gives the information of the depth. Okay, so using Doppler and those type of techniques. So I'm not going into details of that. I'm not a very expert of this domain also. But what I try to say you, or what I try to convey to all of you, uh, uh, okay, is that these multiple modalities are indeed required, right? And that gives a it gives a very good information, okay, depending on the type of the disease, depending on the type of the organ, uh, depending on the which type of feature the doctor wants to investigate. And so we have a plethora of this type of modalities techniques, and okay, and we can have a little bit a gross type of classification that which modalities works for which type of organs, okay, or which type of diseases. Okay, so now that means as we actually work with the data, right? And so so for us, it is very important that the data should be well preserved, and the data should be uh, that means have a standard of the way it will be. Uh, um, uh, it's a move into the different uh, domains of processing, right? From the storage domain to the processing domain to the inference domain, right? These are the domains where the data moves, right? And as the data moves, there should be a sort of protocol that how the data moves and how the data are stored in the various stages of this analysis and decision driven by this data. So there are standard data management systems, okay, like PACS, which is called a picture archiving and communication system. Uh, there is also support given by the radiology information systems, and obviously then the fundamental way the data, the form, the way the image is communicated or image is stored is called the DICOM format, right? And these are the very common terms when you try to look into the way the captured images okay are stored and are being processed using the computational engines. Now I go into uh, the discussion of uh, uh, the topic. Okay, what I try to develop, or try to the techniques what I work with, and I try to develop the techniques for the to serve the doctors and radiologists in a better way. So, so a CAD is basically, though it is actually CADD, okay, but sometimes people squeeze the two Ds and tell it's CAD. So CAD is a class of computer system which actually takes obviously the capture and the intelligence part and the inference, intelligent processing, and then the inference part. So capture, processing, and inference, right? So these three are integrated, right? And that is called the CAD. So the goal is to help the doctors, to practitioners, radiologists, to give a better insight of the disease condition of the particular patient, to generate more supportive inference, right? Because okay, we know that that means there are multiple features which are associated with each of the diseases, and so the doctor has to get all the information, right? And the information uh, generation of information through an automated process, one of the focus activity of this CAD. Secondly, the CAD also helps the doctors to identify or to classify the different types of the condition of the particular patient or the particular image, what is being offered to the doctor to the CAD system. The CAD can also classify that, and this classification helps the doctor to understand the category of the patient and try to take a and ourselves help the decision making process also. So there are two steps in this, as I mentioned. One is called computer-aided detection, which is also called as CAD-E. This is called screening radiology. So what it does, it actually tries to identify or detect the sum of the abnormalities or anomalies. Okay, these are all. This is obviously intelligent computing, or this obviously takes care of artificial intelligence and machine learning. But what's the end result of this is that the doctor gets the information in the form of some detailed information or some detailed marking of the images, okay, which helps the doctors to go to the information or to go to the image very quickly, right, and to come to a decision, and that helps to the initial decision making process of the doctor. The second step of that, or which actually goes further into the processing engine or inference engine, is to categorize this particular deformity or anomaly which has been screened. Okay, and that is called computer-aided diagnosis. So, so a visualization of computer-aided diagnosis is something like in the lower image, where you see that it gives a sort of risk information or also the risk prediction, right, of the various detected regions in a given image. So it first detects the region, and then that is the computer-aided detection, and then the further process is that the detected region based on some prior knowledge. This is pretty important, that based on some prior knowledge, and that is what is the need of AI. Okay, so based on some prior knowledge, it tries to analyze or tries to give or predict a sort of risk or a score to the particular to the detected region, and that helps the doctors to focus on a particular region more than the other regions which are there in the particular image. So this works as a very supportive information for the decision making process by the doctor. Okay. And one of the motivation I will add to this is that when we try to work with the group in Peerless Hospital, the issue was that the biopsy, which is one of the confirmatory way of diagnosing the cancer, okay, are done based on some choice of the region from where the biopsy should be done, and this type of uh, risk analysis of the regions gives the doctor a sort of support that, hey, can I? That means it is better to do the biopsy in a region which gives a higher score of risk, because uh, then it will be a more confirmatory, right? And so unwanted biopsies can be reduced. So these are some of the major motivations why computer-aided diagnosis also plays a key role. Okay. Uh, so sorry, I just made the sequence wrong, but that's okay. So now I come to the other part of the discussion. Okay, a more computer science part of this. So this is the domain of machine learning, right? And this is pretty interesting, right? I started this domain. That means pretty in the same time when I started the work with the computer vision and computer-aided diagnostics, because we have to catch up with the present state of the art techniques what are being followed across the world. So machine learning is a technique or is a sort of tool by which we have learned machines. Okay, this is a very simple word, uh, but that is actually we are trying to do. Okay, we are trying to make a dumb machine, okay, a learned machine, right? And how we can do that? Okay, it's called machine learning. So now, what is a dumb machine, right? A dumb machine, okay, that means cannot do anything, okay, except the job what you have you have prescribed the machine to do, right? And it does the same job whatever data you give to the machine, right? It will not change the job. It will not change the way the processes are done, right? That's also the same process by which we tell okay, he's a dumb person. So dumb person normally the way we try to understand, or the dumb I don't mention the name student because it's not good to tell that, but dumb person, we tell that, okay, whatever I tell him or her, okay, he or she does the same thing. Okay, so how many times I make him or her understand, but he or she does the same thing. So that's the way we do that. So the machines are also dumb because it doesn't respond to the change in the data, the change in the environment. The machine only does the job which has been fitted to the machine in sort of some program or some sequence of instructions, whatever way you tell, or some sequence of control flow, right? So these are dumb machines, right? Can a machine can change its strategy, right, based on the scenario, right? And that I can tell it's a learned machine. Now, this is pretty obvious in our real world, right? In our real world, right, our real physical systems, our biological systems, right, gets modified or changes the strategy depending on the environment. So if a machine can do that also, then I tell that a machine, from a dumb machine, it has become a learned machine. Though to do that, somebody has to help the machine, and that help is called the learning strategy. So there should be so so to gather any knowledge, okay, we require a learning. So similarly, if a machine has to acquire knowledge, right, it has to learn. Okay, how the machine can learn? The machine can learn from the existing data, right? Right, from the existing data it can learn, and then it can use that knowledge to work with the new data which it will process. So that's the entire story of machine learning in a very brief way. So first there is a learning phase. Through the learning phase, the machine develops the knowledge, okay, or gains intelligence in the terms of AI. Though there are different type of AI systems which doesn't go through the learning process. There may be some sort of rule-based decision-making path. So Arthur Samuels and Tom Michels actually gave very two different opinions, but actually they told about two different dimensions of machine learning models or machine learning systems. So what Arthur Samuels has been recognized as the father of machine learning. So what he tried to say, or what he tried to convey, is that the present programmed machines are basically not learned machines. They are programmed, okay, based on some sort of conceptual understanding of the domain, and then that concept is only hard coded in the system, and that concept goes on and on for the lifelong of the years, lifetime of the machine. Whatever happens to the environment where the machine is working, right? So the machine cannot adapt with the environment. The machine goes on and on with the same strategy because this machine is explicitly programmed. Now there will be machines which will actually work in a different way, right? And that was the machine which has learned and which has performed based on the learning. The other aspect of machine learning path was proposed by Tom Michels, okay, where he proposed that the characteristics of the machine learning models will be that it will improve its performance through experience. This is a very vital proposition, which actually gives a direct insight on the data which is used to make this machine to make the learning of these machines. So it means that a machine which has more experience means that a machine which has whose knowledge has been developed through more rigorous training process to make rigorous the learning will be better, right? And if the learning of the machine is better, okay, the machine will have a better performance. So if you were so we have to understand 2-3 things here. One is the one I told, this is I said as term training. So training is the operation, okay, which we perform by the data which exists in the domain. So we train the machine with the existing data in the domain, right? And we try to generate a model, and that model tries to find a sort of learning parameters, tries to extract the learning parameters based on which the knowledge inherent in the data can be trapped. So training, learning, and knowledge development are very is a progress. So through training, a machine learns, and by a continuous process of training, or by learning a huge amount of data, which is similar thing, the knowledge base of the machine develops. And once the knowledge base of the machine develops, the machine can actually work very intelligent way. So the way it can work is something like this, okay? So we push the data to the machine, right? And machine tries to understand the data, and the understanding the data is basically called a process called feature extraction, right? And obviously we need to do some sort of better way of understanding the feature, right? Better and better way of understanding the feature. So if I can understand the data features in the best way, then obviously my decision for the data will be very best. So that's the process of feature extraction and feature optimization, which goes on in the process of learning, right? And ultimately, we can actually build an engine, which I have shown here as a classification engine, but it can also be a prediction engine. So we build an inference engine. So this particular engine is called an inference engine, which I built, right? So this is okay. If it is yeah. So this is called an inference engine I built, right? So this part is understanding the features from the data, okay, and trying to develop the classification algorithm is called the training part. Once I develop the classification engine, right, then it will be an inference model by which the machine can go on and on. And this is same true for prediction. Difference between prediction and classification is that in the case of prediction, my outcome, okay, my outcome may be maybe within a large range, right, and it can be continuous. So prediction is basically for the values, right? I can predict the rainfall, okay, of a particular city, right, by taking the data of its temperature, humidity, wind change, some other data for the last 10 years, and I can now make a prediction model where you just give the current data of a day, and it will try to predict what can be the rainfall amount. But classification is more categorical. So classification works better for the cases like this is diagnosis, where I tell that, okay, whether this particular deformity exists or not, or whether this is deformity of class A or class B or class C or class D. So that's the difference between a classification and a prediction in a very brief way. Now, when we go core into this particular concept of ML for CAD, right, there are 3 strategies, right, that it will take me some hours to explain each strategy in details. But what I want to tell you here is that these 3 strategies are very well used, okay? Now, the first strategy, which is a supervised learning, this strategy tells you that the term supervised means that I have a hand-holding. So supervised handholds a student or disciple in the knowledge transfer process. So there should be some sort of well-defined knowledge which is offered to you, and you just try to explore the knowledge, okay, and try to develop your own knowledge, right? And that's called a supervised learning. So in the case of supervised learning, the training term is very very connected. So what do we try to do? We try to have labeled information. Labeled information means that if I am trying to suppose this is a brain MRI image, and if I try to tell that, hey, that means we have to find whether the brain MRI image is the ultimate of our task is to, given a brain MRI image, my machine learning model will tell me that whether this brain MRI has a tumor or not. So if I have to develop this model, what is the training here? The training here is that I have to have a set of data, which is called a training data set, right? This is a set of data, training data set. And in each of the training data set, okay, a doctor or a specialist has marked that yes or no. It has been labeled yes, okay, or it has been labeled no. So this means that this is a labeled data set which a doctor or which a specialist has already categorized each of the data which you can use for training. Okay, now you have to gather the knowledge, okay, which is there in the information, and we have to find that how the knowledge leads to the decision yes or decision no. And this from the data to the decision, okay, generation of this is called the knowledge development. And once we develop this knowledge using the training data, okay, your model is done. And then your model is fine to accept any unseen data, unknown data, right? Okay, that, and to classify that into yes or no. Okay, maybe diagnostic class 1 and diagnostic class 2. So this is the process of supervised learning, right? You need to have a label data which is already categorized, okay, use that knowledge and try to generate the knowledge or the hypothesis by which this decision can be taken. And once you are satisfied that, okay, that means we have trained enough and there is a process by which we can find the accuracy of your model. Once you're satisfied with the accuracy of your model, then your model can have a real go. Now, if we go to unsupervised learning, this is a different ball game. In the unsupervised learning, okay, you don't have the that you don't cherish, okay, that this handholding. Though you have a huge amount of data, right? You have these brain MRIs, right? You have these brain MRIs, but nobody has mocked this, that okay, this MRI is of class 1 or or having tumor, and this MRI doesn't have tumor. So you don't have this information, though you have a huge amount of data. So what do you do now? So this is also a learning, because what you try to do here now, you try to compare each data element with one another, right? And through the comparing, you know that, hey, this image is pretty different than this image, because this image has some structure which is pretty different than this image. So this way you segregate the images, right? And when you're segregating the images, right, you are actually generating the knowledge in the machine, which can at least differentiate between an image which has tumor and which doesn't have tumor. So this is the process is built up, and then you can use the inference engine to do the same job, to run the same thing. But it requires a huge amount of time to do that. So that's why unsupervised learning is sometimes that means you have to invest lot amount of time to do that. Okay, so it's basically pattern identification by which you can tell that, okay, these two data are very similar because their patterns are similar, and these two data are not similar because their patterns are different. And that's the process is called clustering. So if you look at here, so what the model generates, generates the data which are pretty close to one another. So these two data, okay, are pretty close to one another, whereas these two data are pretty different to one another. So which means that this forms the part of the same group, but these two doesn't form the part of the same group. So you can try to form groups in the data, and then you know that, okay, that means you can label these groups, and then you can prepare the machine, and then for the unknown data, it can just tell that, hey, whether the unknown data belongs to this group or this group or this group or this group. Accordingly, you tell that, okay, what is the actual it's actual inference you generate. Okay, so these are the two very classical approaches of machine learning. Now the third approach, called reinforcement learning, which goes above this. So reinforcement learning is which actually takes care of the dynamicity of the data. So though you can have an inference engine, right, but the inference engine can fail a bit, okay, in certain scenarios. So I will give an example, not from the medical domain, but from a different domain, just to understand that what the reinforcement learning means. So suppose you were walking in a night, okay, in a region where the terrain is not even, means it is up and down and up and down, right? And also that means also it is slippery or muddy in places. Okay, but you have to walk. You have to walk from a particular location to another location. How do you do that? Though your model or you already know how to walk in a road, you know that. So your model is either supervised, that will either gather the knowledge to supervised process or to unsupervised process. But knowing that you can walk in a road, the particular scenario is so different. Okay, in a dynamic world, it is so different that you are not able to. It is not a very easy task to follow the same procedure of walking what you do in a normal road, but compared to the example what I told. So how you then walk? So what do? You actually go ahead one step, right, and try to find that whether this step is stable, whether the step is in mud or water or in a solid soil. If it is in a mud and a water, it will just take out your step, right, and try the step in some other direction. Once you get a particular step which is very firm, then you try to go ahead on that direction. Just to know that you have avoided all the terrible stuff in the particular path. So what you are doing, you are actually taking a feedback, okay, taking a feedback in the runtime, okay, in your system, and that feedback is making your system more stronger, more apt, okay, in this particular scenario. So in the other way, you can also tell that, okay, I put a challenge to the student to make the student learn in a better way. So this is actually reinforcement learning, where if you find that, okay, there is some complicacy in the domain, right? There are some complicated medical history which was not being traced earlier, right? And then you have applied some drug, whether you accept that this particular drug is fine or this particular drug is not fine, or you applied some sort of treatment, right? Or you apply some sort of strategy, some form, right? So that particular effect, if the effect is positive, we call it a benefit. If it's a benefit, you actually go ahead with the strategy, and the strategy gets binded with the model. Okay, so it's called the policy network. The policy gets updated. The policy gets updated whenever there is a benefit. So you measure an outcome. If the outcome gives a benefit, you choose and apply action. So you first do an action, measure whether it's a benefit or a penalty. If it's a benefit, okay, you consolidate this action. If it is a penalty, you just try to lose out this action. And this way, ultimately, your strategy will consist of those actions which really gave you a good benefit, right? And this is also practiced in the process of reinforcement learning. So now I'll quickly go on to, I'm just closing in within 5 to 10 minutes, right? It is okay if I close within 5 to 10 minutes?
Yes,
okay.
sir.
Perfect. Okay. So I hope I have given you some insight of of the machine learning, and basically when we try to tell about medical imaging tasks, what are the tasks? One task will be classification task, as I gave some good examples, right? Okay, you can tell that, okay, lesion is present, lesion is not present. Okay, it may be, it is malignant or it's benign. Another one is detection. Okay, that means I tell that whether there is this particular, whether a tumor is there in this particular image. So detect the tumor and you localize the tumor. Okay, segmentation. Okay, that means a doctor doesn't want to see the other things. He or she just want to get the information of a specific region of the image. So it's called information of a substructure and that is being taken care by the process of segmentation. And last but not the least, as I already gave you the concept of multimodal imaging. So multimodal imaging means image coming from different sources. Now multimodal imaging is coming from different sources, but in normal way, okay, registration is also required when the image comes from the same source but at two different times. Say day 7 and day 17th. Okay, the patient is going through a medical process. Okay, I capture an image in day 7 and I capture an image in day 17th, right? So how I compare these two images? If I have to compare these two images, I have to register both the images in a particular common information plane, right? And that's possible registration. Again, I cannot discuss very details of this because due to a limitation of time, but these are all the areas which we actually do using the computation algorithms. So you see some of the things I have shown here. Okay, so detection, segmentation, classification, something like this, and I will go into more when I show our work. And now I come into the another advanced section of deep learning, where machine learning, which is called deep learning. So machine learning, okay, is actually it abstracts the data information in one particular way, which is basically called a two-step process. So we try to first take the feature, right? First we try to abstract the feature in one particular way, and then we try to use the feature to develop the inference engine, right? But in the case of deep learning, it is an integrated process. The integrated process is that it actually does the feature extraction and then pushing it to the inference engine in a seamless way. And it takes care, it actually works in a very different, a particular strategy of machine learning, which is called neural network. So neural network, actually, if we see this particular particular arrangement, right? Okay, this can be considered as a neurons. Right? Neurons are nothing but your initial neurons, nothing but your data sources, which are nothing but some data points which are collected, or maybe all the data points which are collected from the image of the cat. Now, these data points are analyzed into multiple domains, into multiple feature space, very similarly like that of the brain. In the brain also, we have different functional regions, and each functional region tries to abstract a different type of information out of the data. And this is also the same thing. So what it does, it goes from the initial data space to multiple feature spaces, and then it tries to concatenate all the feature space at the last stage to ultimately define the classification. So this is a process which is very holistic. This is a process which can work with a lot of complex complex classification or prediction problems. But what it actually requires, it requires some sort of good system to execute these algorithms, because the algorithms are computationally very heavy algorithms, and we require a lot of parallel processing to accelerate this type of algorithms. And secondly, as the feature extraction process is also combined with the inference process, or the classification prediction process, to train this type of systems, you require a good amount of data. Okay, actually much larger amount of data than traditional machine learning techniques. So this is what it actually looks like in the stage. So what it does, it actually tries to work on the different different information planes, right? So each of this, okay, each of this structures represent one information plane. Okay, So it tries to map the data in different information planes, right? And each of the information planes ultimately con, okay, contributes to the ultimate decisions. And this actually uh, goes on with compression and with analysis in a sequence. So this may be a larger information, but this is scaled down into the pooling layers, into a very concentrated information, so very compressed information. Again, this compressed information is analyzed again to a next level of feature space, right? And this goes on and goes on up to a certain depth, and that's why it's called a deep network, because it is a processing which involves layers, okay, right? And ultimately the decision is taken based on the very concentrated feature space, or compressed feature space, which gives a very very deep insight about the okay, about the object, right? And that's the way how the deep network works. Okay, and deep networks have several uh, uh, several implications or several advantages, right? It is called towards precision and automated diagnostics. That means the uh, the the way we develop this particular deep network programs is that we don't have to have much knowledge about the domain, right? Actually, many of the people just blankly run there, which is not good, right? Okay, it is not correct to just tell that, okay, we don't understand anything of the domain, I just pass it to a network, right? A network will give me some result, and the based on that result I can take a decision. It's not entirely like that, because when the decision is generated, right, you have to analyze the decision, and accordingly you need to adjust your network where the decision is actually okay, it's going higher in the in terms of error, or it is lowering the error, right? You have to understand the measures in the particular domain by which we define that uh, this is more okay, uh, this outcome has a more error, or this outcome has a less error. So it is not oblivion about the domain, right? but it doesn't, okay, it doesn't takes your much input in terms of understanding that the various nitty-gritties of the domain, right? So that's why deep network helps in that particular way. Okay, now I will quickly sum up within the last 5 minutes or so. I will quickly sum up about the work what we are doing. I cannot discuss about the techniques here due to limitation of time, because my motivation here was that there are biologists, okay, and computer scientists, okay, if they join hand, they can do fantastic things. Okay, I am only showing, okay, a very small window, right? What I have achieved in the in the in the in the 6 years, okay, or so. But there are many experts, okay, who are working in different domains, and obviously, okay, that means I can also get into some new domains if I can find a suitable problem where I can contribute. So let's look into some of the work what I have done. So this is one of the very phenomenal work done by our group for the last 5+ years. This is the work which we do with the Peerless Group of Hospital, and obviously Dr. Mujit the core. She's a great academician, a great doctor, okay, a great collaborator. She helps me to work in this particular domain, and she's from PLS Hospital, though she's connected with different higher education institutes. So what we have done, we have done the. So I will go with one by one. So we have developed the first lung database in India. So our group, that is the Calcutta University Center of Excellence. This is actually, this project is supported by a Center of Excellence in the Technology Campus Salt Lake of our university, which is being funded by the TEQIP program of Ministry of HRD. Okay, so this particular, we have that means my student and the group from PLS have taken enough pain to to capture the data, annotate the data by the doctors, okay, and then to transform the data into a database which is fully annotated and which can be fully searched. So we have actually this is the total brief of the summary of the data set. This is the way we have okay, that doctors have helped us to annotate that so that the informations are labeled. The data set, these are the sample images you can get in the data, and you can get the uh, different types of annotations for the disease information in each of the images. And this is a sample template which is not still open in the public. This is now opened in the okay, based on the requests. Based on the request, we open, because we didn't have the copyright still. So we are now going for the copyright. Maybe within 3 to 6 months, this will be up in the public domain. Because now putting a database in the public domain, that is, if you don't protect your copyright, it will be a disastrous. Okay, so this is the work we have done, and we take the credit of being the first group in India who have generated a database for lung from Indian patients. But actually, from South Asian, we have seen that the data of lung for the South Asian community is pretty less. Okay, the most of the lung data are from the community from US and Europe. So this is also a phenomenal contribution in the domain of South Asian data also. Okay. What we have done, we have actually developed techniques by which we can automatically detect the pulmonary nodules, okay, from the HR high resolution CT images. So this is some sort of flow diagram we have done. So we use a sort of okay, first of all, some sort of feature extraction. This place and this place is the classification. So we do the feature extraction followed by detection. Sorry, segmentation. It's a classification. It's a segmentation. Okay, and next the classification, I will show what we have done. So this helps us to the detection of the nodule, and we have used some sort of intelligent technique in feature selection based on particle swarm optimization. And you see that these are the well segmented images. These are the segmented images which we have got for the nodules of the lung in lung CT images in a okay, we have shown in a little bit low dimensional form to fit it in the presentation. And these are the magnified form what you can do. Okay, you see the nodules which are okay, which are here. Okay, a nodule which is here can be actually has been marked here. Okay, a nodule which is here, right, has been captured very well here. So you see the results of segmentation, okay, of this. Okay, this is the ground truth, and this you can actually capture through my tool. So you see, and okay, that means, and there are 2 papers we have done. We have actually recently got published on this work. One is on Elsevier biocybernetics and biomedical engineering, another one in computers and electrical. Though these 2 are very good journals in the terms of infrafactor and scientific outcome. So a good point in this work is also that we have been able to detect the nodules which are of sub-centimeter dimension. So sub-centimeter dimension nodules are sometimes they go out of the site. That means they are not. Sometimes the doctors also miss those nodules. But our detection strategy was very much very well appreciated because in this particular paper we have this particular work we have successfully detected the sub-centimeter nodules. Okay. So this is a software which we are doing, and this is almost done. We are also going for a copyright of the software. This is called a software called PulmoCare, right? Obviously, this particular work has also a sort of classification. Sorry, I missed this particular table. So our work not only detects but also classifies the risk of the nodules based on the various features, feature categories, right? And this is called the risk assessment also. So these two components of our tool, which is given a lung CT image, I can detect the nodule, localize the nodule, and then I can do the risk assessment of the nodule based on the features. So first part is segmentation, and the second part is some sort of classification. So this total tool will be is under trial at PLS, and is called a PalmoCare, which is again a joint activity of our group with the PLS hospital. Second work is something on a work which we started with the neurosciences Bangur in the SSKM hospital. And this is a sort of segmentation technique for the brain MRI, right? We have used a sort of it's energy-based model to segment out the lesions in the brain. Okay, and these are the good results we have got. In our work, and this has recently got accepted in one of the top journals of IIT image processing. And the way we have done is actually we have actually extracted the features in a random walk strategy. In random walk strategy, we are analyzing the energy values, right? And then we are trying to classify the regions based on those energy values. Okay, so we have trained our model at first, and then we have used that. So the good point is that it is the automatic segmentation, means that many of the algorithms works in a way that the doctor looks into the MRI and marks a region, and that generates a seed value, and based on the seed value, the segments are being generated. But in our case, segments are generated in an automated way. Okay, basically for the lesions. This is another work what we have done. This is also on the spine MRI. The problem in the spine is that when we do the MRI of the spine, right, you take a three-dimensional data in the three dimensions of the plane, like coronal, axial, sagittal. It's a very large amount of data, right? And it takes a lot of amount of time. Due to this large amount of time, the doctors remain busy, and the machine remains busy. And for that also, the service of the machines to the more number of patients is not possible. And in some cases, the cost of the machine also increases. So this is a very good problem which was given to us by one of the neurosurgeons, whether you can do some sort of optimization in this type of image generation or image reconstruction. So we did actually that work. So we developed our own reconstruction algorithm, right? This was something first of its kind in India, right? We have had a copyright in 2017 there, okay, in this particular. So we have successfully generated the 3D reconstruction. Not only that, we have successfully generated the 3D reconstruction, okay, from the image in a single plane. So you don't need to give me the images of all the three planes. You give me the image of any one plane. Okay, I will generate the image of the entire volume. That means the information of the entire volume. Though there is a little bit caveat here. The caveat here is that obviously when we are trying to generate the information, we are regenerating information between the spaces. That's the trick. But we're doing it in the best possible way. But obviously there will be some sort of information gap, and if your dimensions are lower than the information gap, then it is pretty difficult. But this works pretty good for many of the cases where doctors at the first hand sees that and sees that the dimension is quite good, and so let's do not go for the 3 cuts. Let's go for the 1 cut. Do it fast. Use our tool to generate all the other the entire volume, right? And we're reconstructing in a very good way. Other one was that we also developed our own virtual slicer where the doctor can cut the volume in the different orientations as per his choice. So we first developed this tool, and and published it as a copyright, and then we polished the work a bit in the terms of mathematical concepts and computational concepts, and got it published in IT, the IT image processing, this year. Last, but there are many other works. I could have shown the earlier works what we have done, but these are some recent works, just to highlight what are the recent works we are doing in this domain. So this is a work which is based on deep neural network, and we are trying to segment out the vertebra, the different vertebra segments, right? And this is called intervertebral disc identification. This is a very challenging problem. This was posted by Mikai. Mikai is one of the top conference in the medical image processing, where doctors, radiologists, surgeons, and computer scientists joined hands and developed these computational strategies. So this was a Mikai challenge in 2018 to segment the various vertebra, in a given MRI, right? And we have successfully done that using a deep network and some sort of a modification of the standard deep neural network. And this work is just under revision. We are very hopeful that we'll get this work published. So, due to the interest of time, I'm trying to just what I try to tell you is that the horizons, the horizons what we have in the machine learning and biomedical in terms of disease detection and disease diagnosis, though we have miles to go, and a lot of good groups across the world, are working in this direction. And I hope that through this type of interactions, which is a really wonderful interaction, that means to build the community, to know each other work, to know that what's the contribution I can do in one's code domain, or what are the contribution one can do in my code domain, and how we can both collaborate. And this is very good for the students also to work with not only his or her supervisor, but can also communicate and collaborate with the people from cross domains. So so this motivation, I just want to propose to the August audience here that so the image analysis in the medical image analysis is driving towards a data-driven medicine or data-driven therapeutics. It has challenges. It has many challenges. I will just tell one challenge. One of the most challenges is getting the data right, because when you drive your when you make a learning model, your data should be very good. If you're not working with a good data, right, your model will be bad, and you cannot work with that model. Now, who will tell me that this is a good data? I am not the expert in the domain of medicine or biology. I need an expert in the domain of medicine and biology, or a doctor, or a biologist, or a biochemist expert, right, or radiologist, who will tell that, hey, this is a good data. And then the next step, right? What I need to do with the data? What is the actual problem? What is the medical problem? Who will give it to me? This will again come from the domain experts. So domain experts will tell me that this is the medical problem. Then I have to formulate that problem as a computational task, and then I have to go to my domain. And I can work in my domain with some very interesting techniques. But again, I have to come back. What I have done, whether it suits the requirement. So what I have done, whether I have understood the problem in a proper way and have done a proper solution, whether the solution helps the domain experts. If not, it will be just thrown away. So you see that there is a cycle, right? And also in the intermediate stages of development, right, I require some sort of help and communication with the experts, so that there are certain things I need to clarify in developing my own technique. So this is though I work in the computation technique, but I require a real help and real support from the people in biology, in medicine, in surgery, in radiology. And that's only we can work together and do this thing. So there are many challenges, but the challenges can be overcome if the people from interdisciplinary cross-domain work and try to solve some real problem. Yeah, obviously traditional machine learning has scaled up to deep learning, and obviously we can look into those areas of deep learning and can try to find whether we can solve some new challenges using the deep learning. Okay, I want to thank my students. There are more couple of students in the group. I didn't get their photos. I didn't put here. So they work in various activities. Okay, in the various city, digital X-ray, brain MRI, spine MRI. Okay, and that means, and our students, okay, are very good, and they're contributing really well. And I am also hopeful that that the people here will also try to connect with me, and we can set up some new collaborations okay, using this platform. And thanks. And so I finish my lecture, and now I am open to the audience for any questions. I hope I have been within the time.
Yes, sir. Thank you so much, sir, for your such an enlightening talk. And we have a question in the YouTube chat box. So shall we go ahead with that?
Sure, sure. So I am making my stopping my sharing. Okay.
Yeah, sure.
Perfect.
So the first
Yes, I
question
will be
is
happy to take
from
some questions.
Sir. So the first question is from Prabhat Kumar Swain. Uh, he is asking how AI and ML techniques help physicians to predict tissue and organ dysfunction to improve the efficiency of healthcare services.
Okay, great. So the way we look into the problem is that means we need to have our data in some form, right? So dysfunction of organs, okay, can be taken by some electron, okay, say okay, okay, so the EEG data can be there. One form of data can be EEG. One form of data, there are many different types of okay, so X-ray data can be there, one form. So we need to actually okay, so understand the data what is required, or the doctors okay, so use to get the information about the mobility of an organ, or the functionality of an organ or the tissue. And then obviously we need to generate, okay, we need to generate a knowledge, okay, from that. So that can only be possible, right, if we can build a sort of, that means if I have a corpus, okay, either a label data set, right, or I can have a very well annotated okay, information exchange with the experts. So the AI and ML can help you, okay, only if you can tell that this is the information which I need to have in my inference. This is the intelligence. Sorry, this is the intelligence I need to have in my inference. So I need to understand that what inference you require, right, and what is the source of the data, right, and from that we have to, if there is already existing uh, uh, data, okay, which has the inference, okay, I can use that, right, and I can use that in my learning, and I can develop my model, right. Otherwise I have to have a constant iteration. There are also statistical techniques which can also play a great role. In fact, we have in Department of Statistics, we have some faculty members who are also working in this domain, not exactly through ML techniques, but through statistical techniques. So there should be either statistical techniques works with measures, right? So ML techniques works with the data. So it can help in a great way, provided we have a pathway from data to the inference. That I want to say.
Yeah. So So he's also asking that is there any successful outcome of AI ML based treatment of diseases in India at present context?
Yeah, there are a lot of, that means at the present scenario, uh, okay, that means the softwares the doctors are using, right? There are a lot of, activities are being going on in the domain of radiology, right? I cannot tell in the other domains, but I know that, uh, okay, that means in the recent uh, okay, in the recent COVID scenario also, if you see that uh, the chest city based detection policies, right? So so the policies are being well defined, that okay, this is the chest city and this is the way this has been done. So whether the doctors are taking it in a very strong way, or doctors are taking it in a okay, in some way, okay, that actually varies, because okay, because that depends on that what is the way the doctor views, because this is a sort of secondary instrument still. Okay, still in India, okay, we don't have a tool which prescribes something to the patient. Okay, the medical prescription cannot be defined by a tool, right? But now the doctors uses these techniques to just to have a support on their decision, may not be the decisive decision still now. But but we all hope that across the world, uh, the scenario is getting very well progressed in this particular domain. And I know that uh, there are now teams which are which are catering the needs of the radiology findings which have happened in different parts of the world. There are some companies in Bangalore, right, who are working for the medical hospitals in US. So they are transferring the data, and the tools are doing a pre-screening, and then they are involving the doctors to do the final confirmatory process. So these are the ways they are now using the tool. uh, but I think slowly and steadily, uh, there may be some day that when the tool can okay, that means obviously that depends on all the medical ethics and all the medical, okay, okay, the standard and approvals. But the tool will be intelligent enough uh, to predict or detect something which might be a very difficult proposition for a doctor.
Okay. So the next question is from Shanchari Gorai. She's asking nowadays proteomics are playing great role in the detection and therapeutics approach for a disease like cancer. So she wants to know if there is any role of AI ML in this study.
Excellent. Yeah, there are a lot of people are working in this domain, where they are studying this network analysis they call, and they're trying to understand the features of these networks. Okay, and obviously that means it comes under a very interesting domain of bioinformatics. Okay, it's the class of bioinformatics have come up, which is called proteomics. Okay, and where they try to understand the uh, data which is already there, which is already done by some experiments, and tries to predict the diseases. Okay, and this is a very well established field which is emerging. So uh, so the only thing is that, okay, if you want to find some information, some pattern, okay, in the data, and use that for your future inference, okay, then AI and ML can play a great role.
Okay, sir. So the last question, as we are running short of time. So last question is from Gaurav Chatterjee. He is asking that are AI ML techniques are beneficial in detecting any new form of disease which are not known?
Oh, this is a good, very good question, Gaurav. Okay. Uh, so, so if we see the techniques which are coming up now, like the deep reinforcement learning, okay, or there are some techniques called generative adversarial networks, right, which can try to find out the the very minor differences, okay, between the standard data, okay, and data which is generated, right. So now detecting of disease is basically outliers. So maybe the categorization of disease, it still requires a lot of other confirmation from the medical domain, but what AI and ML can do, ML can find out the outliers in the disease data, right? And these outliers can lead to the identification of the disease, okay, say in course of time, or more, okay, it's a data from the other experimental domains.
Okay, sir. So thank you, sir, for taking on
Thank
the
you, Nandita.
questions and explaining it so nicely. So now I would request Professor Enare Banerjee to join us to close the session. So, ma'am, over to you.
Thank you. Thank you, Nandita. I was absolutely fascinated with your talk, Amlan, and we have learned so many new things. And you have taken the time to explain it so nicely. You have broken it down into comprehensible units, especially for people who are not conversant with data science. So I completely appreciate the need for such cross-disciplinary transgressions, so that ultimately the basic pattern of what is going on in something as complex as a biological system becomes a little more understandable. So thank you so much for today's session, and thank you so much to all the audiences who joined in with progress and prospects in biology. And once again we learn the new disciplines that are emerging. And Omlan, I have a question for you.
Sure.
So this is a sort of a cross between basic biology and translational biology, and then somewhere the data analysis is coming in. For example, when a huge body of data is generated from a complex system, it is very difficult to draw any deterministic or even probabilistic conclusion from it. So, of course, a pattern is emerging from the kind of work that you just described. Now, my question to you is, this is for imaging. What other areas would you say? For example, we found from one of the questions, and you explained very nicely with the outliers. So, my question to you is, what would be the possibilities, for example, where the kind of research you do could further expand into, where the
Oh,
biologists may look for such kind of collaborations?
oh, great. So we are working on another project. I didn't describe it much, limitation of time. We are working on another project which is on body signals. So we are trying to. There are nowadays there are sensors are really very great. Okay, we have different kinds of sensors which can sense different types of body signals. We are working on one type of body signal which is called heart and lung sound, right? And that heart and lung sound, okay, actually give you, actually in the COVID also, okay, in the present pandemic of COVID also, it is some sort of marker. So we are using a sensor, and we are also working with the very common sensors like ECG. Uh, we had done a good work in 2017 with University of Southampton, UK. Okay, where what we have done, I will try to see what are the other type of signals we can process. So we have used a sort of signals, visual signals from autistic child, right? So autistic child, we know it is basically we need to train them or interact with them in a in a okay, in a very comfortable way, and it's very difficult to understand the autistic nature of the child. And in the early years, if in the early years the autistic nature is identified, then we can actually take some good steps, uh, so that he or she can be well supported. uh, Now we find out the EEG signals, okay, has a particular pattern, okay, when I give some visual objects, okay, to autistic child compared to the other childs. And we try to analyze this in a concept called network analysis. So network analysis is something that we try to take some data as nodes, right, and try to see the fluctuations between the data in the nodes. So this generates a dynamic graph, right, and this dynamic graph can give you a lot of insights. And the same thing, a little bit same thing, we recently tried in a particular system on analyzing this ECG. What we found out is that it computes it much lesser time, than the domain than the existing way. So there are some existing domains also, not only new domains. There are some existing domains also, where if you can actually try to understand the complexity or the actual features by the help of the okay, yeah, experts from the biology domain. And then if we can try to find out that is how the data generated can be used in a better way, to solve the problem in a simpler way, in a faster way, that also helps in a very good way. And in this particular project, actually this recent project, Professor Anjan Das Gupta of Department of Biochemistry, okay, of our university, yeah, that means has helped me to understand the domain, and then I tried to uh, uh, okay, try to work with that computational part. So these are the very beautiful collaborations we can do. That means uh, with the biologist, and basically the where we are trying to have a huge amount of data, where we're trying to find some patterns and try to have computation because computation, I tell that computation is not a domain of only computer scientists. Computation is a domain of everybody, because it is a generic logic, right? Maybe some core algorithms we get trained to work with that, and we can jump into that faster. But I think computation everybody understands. Every scientist is just understands computation. So if we can have an integration, have a sort of, I think we should set up some courses, okay, which will be like okay, that means I am working with that the problem in botany. I will tell you later this. It is called okay, that means I'm like, digital geometry and botany, how they can club, right? And we can generate some phenotypic features, okay, of the plant very fast using those techniques. So I'm trying to explore those areas now. Okay,
Oh, that is
I'm always
absolutely
welcome.
fascinating.
Yeah.
So I think this is an excellent platform, and PPB is happy to connect, potential areas of collaboration. And like our speaker, Professor Chakrabarti, described today, I think the possibilities are endless. And we just need to explore, have these cross dialogues, and some circuit which was probably never not even conceived of before can be generated, and a new line of thought can be initiated. So, on that happy note, thank you once again for such an illuminating talk, and thank you to all the participants who joined in tonight. And like I said, let this be a platform which will facilitate connections of mind, new ideas that can come out of works of individuals. And I guess exploration is a continuing process of mankind. And in the virtual domain, like never before, we are foraying into that. So, with that, we should conclude tonight's lecture. Thank you to the speaker, and thank you to all the participants who have joined in live today and who will doubtless be watching Professor Chakrabarti's talk in the future that shall be archived. Thank you.
Thanks, Professor Banerjee, and thanks to all the participants. Thanks, Nundita, the organizers. Okay. Thank you all. Good night to all of you.
Thank you, sir. Thank you, sir.
Good night.
Thank you, everyone, for joining us. Please join us tomorrow in our regular Sunday webinar by Professor Tanya Das from Bose Institute. Thank you once again. See you tomorrow.